All right, guys. So, how about those derivatives?
Some of those were getting pretty
hairy.
pretty lengthy.
Yeah. Did y'all check them?
Yes.
Yeah.
You feeling good about what you know, don't know? Okay. If you feel good about those, you're in great shape for this test in terms of taking a derivative. There are a couple other things you're going to need to know that we're going to talk about today. And then I believe, don't we just review Monday? Oh, no, we don't really have a review, but I give you some random AP problems and some miscellaneous stuff, and then we take our first test Tuesday. So there's not like a formal review, I don't think, but there will be a test on Tuesday over everything leading up to this point. And then the only thing I'm going to add to that, on Wednesday, I'm going to talk about trig derivatives, and we're going to do trig derivatives and then talk about how that works with everything. And actually, I'm going to probably do a video because I won't be here that Wednesday, but I'll leave you a trig video over a video of a trig derivatives for this class. I'll record it from first period, but I have to leave after fourth. And then we're going to talk about a couple of other things with piecewise functions, yada, 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 a bunch of other stuff, and then do some more review. And then we're going to talk about how you can use your calculator. Your calculator actually can't find a formula for a derivative. So it can't do what you can do in terms of like f prime of x and then write it, use all your rules. It won't do that for you. But if you ever need to know a derivative at like x equals 3, you know how you normally would take the derivative and plug a 3 in? Your calculator can do that. So if you have a function in your calculator, maybe as an equation or whatever, as a graph or whatever, you can actually ddx and write the function out and then type in like x equals 4 and your calculator will spit out the value. So we're going to talk about that and then we'll have our second test. And hopefully the grades will be pretty good on both of them. They typically are. So anybody if you don't have a particular question, well, there's 2 new topics we're going to talk about today. They're not overly difficult. And I think you'll be fine on both. Typically, people are. Any question on anything up to this point? So you know how to take a derivative of a natural log, a derivative of an e to the something, and then a derivative of a log-based something, or a derivative of a base, say, 4 exponential function. You're comfortable with all those? How to do the chain rule, all that kind of stuff? Okay. If you're not, say something, we'll do them. We'll do something. So here's the things we're going to talk about today. First thing is where graphs are differentiable. Now, the word differentiable, if you remember back from the very first day, I said there's different ways to ask you to do a derivative. One of them might be like find the slope of a line tangent to a curve. Well, finding the slope where it's tangent would be a derivative. Another way to say it is f prime of x, right? Another way to say it is dy dx. There's all kind of ways. Well, another way I said, if you look back, is I said differentiate the function. And to differentiate the function means to take the derivative. Well, if I asked you, where is a graph differentiable? I'm asking you, where would you be able to take a derivative? At what places? So if I asked you, is a function differentiable at a certain place, you would have to be able to essentially have a tangent line there. Well, sometimes a tangent line at a place doesn't make any sense. And here are the 4 places where it doesn't. And keep in mind, when you think about why it does and why it doesn't, keep in mind that what does a derivative come from? It comes from a slope. But what was the definition we used to come up with? We used a what? A limit. And we started with the secant line, and then we created a tangent line by doing a limit, right? We squeezed that h value to nothing, right? So a limit, what has to be true? You have to be approaching what? On a limit. The same y value from both sides. So when you think about if something's differentiable, you have to be able to squeeze that second point towards the first point from both sides to create that tangent line. Well, there are some places where that doesn't work. Okay? Also, if it's a derivative, it's a slope. A slope has to be defined to actually exist, right? And there are tons of slopes that are undefined anytime I get what in the denominator? A 0. Then that's undefined. So here are the places where a derivative would make sense. And I think about them as 4 separate places. And some of them have names, some of them don't. First one is called a corner. The most famous corner is the place on a absolute value graph where you see a sudden switch in directions. And you can see right here, the slope here was -1, and the slope here was +1. But actually, it doesn't have to be just a sudden change. It can be any time it change. Well, it's a sudden change, but it can be any change. It doesn't have to go from like -1 to +1. It could do something like this. I could be cruising along right here and then just suddenly switch direction. I could be going straight and suddenly head down in a certain way. But any place that seems like a car couldn't make that move. Like if I'm in a car and I'm cruising along, can I just stop and then suddenly go immediately left? What do I have to do? I have to curve to go left, right? Even though a road might look like that, the car's path would curve. So I can't just stop, rotate on an axis and head a different way. And even if it's really subtle, like even if it was just, I'm coming like this and then I make a sudden, but yet subtle change. Cars can't just shift like this and then head in a different direction. It's got to be smooth. So a sudden change like that, where basically the slope from one side is different from the slope from the other side at that spot. So the slope coming in right here, you can see it's different. Even if I did the little limit definition, even if I bring this point closer and closer and closer, this slope, and then I bring this point closer and closer and closer, this slope, they're different. So even if I use that definition that I told you where there's P and I take Q and it's H apart and I bring it closer, that slope as I near there and this slope as I near here, different slopes. So if you have different slopes from both sides, it's called a corner. Can't take a derivative there. Not to mention, if I were to say draw a tangent line, I could draw that's tangent, that's tangent, that's tangent, that's tangent. There's all kinds of them, right? So I got all kinds of slopes. Well, that doesn't make sense. It would have to be one slope if it was one tangent line. So corners, if you ever see a corner, whether it looks like that or that or that or whatever, we say that it's not differentiable there. There is no derivative. That's the first one. Second one, cusp. Now a cusp is similar to a corner, and you might look at it and go, it looks exactly the same except the line's curved. Well, at first glance it does, but check this out. What if I go to my calculator, my new improved TI Inspire, which this does not appear to want me to do that because it's not on. So I'm going to go to my calculator while we're waiting on that to boot up. And I'm going to type in the graph that you have on your screen, which is x to the 2/3 power. And I think you remember that as the bird function, right? So here is your bird function right here. Come on, man. There we go. I'm zooming in. And this is essentially the graph that I just used on your screen. Now, that I used on your paper. Now, on this graph right here, I would argue if all you knew about this was the picture, it's a corner. Because think about it. What does it look like the slope's doing as you come in? To me, it looks like it's flattening out right there. It looks like it's about like that. And over here, to me, it looks like it's about like that. And I would say, well, that's a slope and that's a slope. They're not the same. Must be a corner. But look what happens when I zoom in on this. When I zoom in, okay, I'm going to actually have to be a little creative because I'm going to zoom in. What are you starting to see happen as I zoom further and further in? It's getting more and more vertical, isn't it? Now, it's hard to really show this super well, but I think you get the idea, right? Every time I zoom, it looks more and more vertical, doesn't it? So what happens is even though, and granted, if you're going, well, how are we supposed to see that? Well, if I drew a crappy enough picture and you said corner when I really meant cusp, I'm going to give it to you. But I usually draw these by hand to kind of emphasize. And when I draw them, I do like this. So I really emphasize that they're going vertical. But what that means is this right here, as my slopes come in, now even right there, the slope has a value, right? It's negative sloped, and it would be really big, right? At maybe negative 20, negative 50, negative 100. I don't know. I mean, this unit, that's a pretty, it's not even one, is way over there. So this is a really steep slope. But the idea is the closer I get, the bigger it gets. And right when I hit 0, what happens? Slope goes vertical and it's undefined. But it does it for one point, and then it instantly basically bounces and reverses direction, becomes a positive slope. So it goes from almost negative infinity to undefined to positive infinity, and then flattens back out maybe, or whatever, depending on the graph. Does that make sense? So basically the slope for one instant went vertical. Now there are two kind of situations where the slope goes vertical. One where it goes vertical and kind of reverses, basically goes from negative to positive, or maybe from positive to negative sloping. And then there's another one where it comes down here like a negative slope might and goes vertical, but then immediately adjusts and stays negative. But we call that where it does that, where it goes vertical for one instant but doesn't change direction. We call that a location where there's a vertical tangent line, because there would be one, a vertical tangent line right there. But if it reverses and then bounces basically and goes the other way, we call that a cusp. So this particular one, the second one I have listed here, we call that a cusp. And I will make that more clear right there than this picture, okay? Because it's really hard to tell right there. If you said corner again, I would be like, that's fine. But the key to the difference between a cusp and a corner is here they're just different slopes. They don't even have to change sign, right? It could say negative and then a different kind of negative. The thing here is it goes and changes signs from a positive to negative, basically infinity. And at that one spot, it's vertical. Okay, that's what makes it a cusp. All right? And to be honest with you, nobody's going to ask you the definition. They're going to ask you to look at a graph and go, hey, what's happening right here? And you would say, oh, there's a cusp right there. And I would say, is that differentiable then? And you'd go, no, it's not differentiable because it's a cusp. You with me? It's continuous. We know that because there's no break in the graph. The limit exists, the value exists, and they're equal, but it's not differentiable because the slopes weren't the same. And for a graph to be differentiable, you have to be able to draw a tangent line right there. And as you bring points in, you should get the same slope. And clearly, as I bring points in towards that point T, using that example we talked about, I would get different slopes there, right? And they would go to infinity. So that's a cusp. The third one is the one I kind of described. It really looks right here. It looks a lot like a cusp, but instead of here, this is what a cusp would do. Instead of coming in here and going boom, and then going the other way like a cusp would, it just comes in there, hits vertical, but then just keeps on going. So it doesn't reverse direction and change sign. But you can see for one instance, what did the slope do? Got bigger, 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 vertical for one moment in time, and then flatten back out. Maybe not completely flat, but just started to flatten back up. We say this, it's going vertical. Some people call it, it has a vertical tangent line. There's no formal name for it, but that is the situation you got to look for. And then the last one, well, if the whole definition of a derivative is the slope of a line that's tangent to a curve, what if there's nothing there at that point? Well, how can you draw a tangent line at a point that doesn't exist? Well, you can't. So any place that it's non-continuous, it doesn't exist there, at least from both sides, right? So even though like this one doesn't exist at all, this actually exists, right? But it's not continuous. So the bottom line is if it's not continuous, even if it exists there, there's a break in the graph at all, can't find a derivative. Because like even right here, if this was point P and this was Q, as I bring Q closer and closer and closer and closer, that secant line becomes that tangent line. But look over here, as I bring Q closer and closer and closer, the secant line becomes that tangent line. Well, they're different and they're not connected. So I can't say that there's a derivative there. So 4 places: corners, cusps, places where the graph might go vertical, which those are kind of sneaky sometimes because I can have this polynomial looking thing cruising along and you're like, oh, it's a polynomial. Everybody's happy. It's nice and continuous. If it's continuous, surely it's differentiable. Not true, because if it goes vertical for one moment, it's not differentiable there. Everywhere else, maybe, not there, right? And then finally, any break in the graph, any place where it's not continuous. So that could be VAs, holes, jumps, or maybe just a place where the graph stops, maybe picks up later. Anywhere in here, it's not continuous, no derivative. You with me? So I'm going to run through 4 graphs real quickly. Hopefully this will not be a big deal. And then trust me, I will probably not refer to this again until your test. So remember to star this or whatever and go back and just brush up on the names, things like that, because I will come back to it. But to me, it's not that big of a deal that I need to test you on it. You'll see what I'm talking about. So check it out. First one, tell me A, is the function differentiable or not? And if it is, tell me why it's, and if it's not, tell me why not. So look at -7. I'm just checking random points here. At -7, does the graph look differentiable? Why not? Looks like a cusp to me. Correct. At -2, does it look like it? It's a pretty crappy drawing. It kind of looks like it's going vertical from the top, but you could have an argument that's not from the bottom. But to me, a better looking graph would probably look like this. That's what I would probably do on a test, and you'd go, oh yeah, that's definitely going vertical right there. Are y'all with me? But I will concede, not a great drawing. What about at x = 3? No, not even a point there. I can't draw a tangent line to a point that's not there, right? Non-continuous. What about at x = 6? No, why not? Not continuous. You don't even have to say jump. The rule is just not continuous for at x = 3 and 6. Look at the second graph. What about at -5? What about at -5? No, not continuous. What about at -1? It looks like a corner. Now you might go, it looks like a cusp from the right. True. But to be a cusp, it has to go vertical from both sides. So even though it might look cusp-like from one side, it's certainly not. It looks like it's approaching maybe 1/2 or something from the left side. Different slopes, cornered. But you can check the video for that second thing. At x = 2, what do you think? No, not continuous. What about at x = 5? Absolutely, right? You can draw a tangent line there. It's defined. It looks like it might be 0. That's even more important. That is a name for that. That means that 5 is a critical number. You'll find out about that in calculus. But yeah, if I get a slope that exists, and there's a point there, of course, that is definitely continuous at 8. What about at x = -7? Or whatever that is. No, why not? There's no left side, so it certainly doesn't continue, right? Discontinuous. What about at x = 0? Yeah, it's slanted right there. If I were to draw a slope in there, looks like it's maybe -1. So yes, definitely continuous at number 10 at 0. What about at x = 3? No, I think I meant for that to be a cusp, but another crappy picture, because from the left, it almost looks like it's slanted straight in there, doesn't it? So if you look right here and you saw that and you went, oh, that slope looks like it's 2. From the right, the slope maybe looks like a cusp. If it doesn't look like a cusp from both sides, you would say corner. But again, I don't even think I get tricky like that in the test. What about at x = 6?
They'll not approach the same.
No, yeah, one of them is going down to an asymptote, but the bottom line is what? Not continuous. There's a break in the graph. And then finally, 13, what about at -6? No, that's like the definition. That's like the picture of the corner right there, right? So no, because a corner. What about at -2? No, because it's not continuous. What about at +2? Definitely yes. And what about at +5?
No.
No, looks like a cusp there. Y'all tracking with me? That's what I would ask you, that kind of stuff. Okay, not a big deal, I don't think. And if you're really also wondering, like back to that original graph, you remember that original graph, the bird graph that looked like x to the 2/3, right? And we were like, well, how can you tell for certain? Well, what would happen if I took the derivative of this? What is the derivative of that?
X to the
-2/3 times x to the what? -1/3. How do I rewrite that? If I were to rewrite it, where would that x to the -1/3 go? In the denominator as a cube root? So if that is my derivative, which I would not need you to simplify that, you're fine to leave it like this. But if you did simplify that, what would the derivative be if I said, hey, now what's the derivative at 0? What happens? Doesn't exist, right? There's no derivative there. That's where that cusp would have been. The reason I'm showing you all these things is because sometimes you don't have the equation to be able to check at 0, right? Sometimes all you have is the picture. So when you look at a picture, you can tell that it's not differentiable if you see one of these 4 things. And remember the last one, there's lots of ways it can be not continuous, right? So if you see one of those, definitely make sure that you understand that you can't take the derivative at that spot. Everywhere else might be great. Like there's an infinite number of spaces here, 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 and here that I can take a derivative. Just not there, 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 or there. You track with me? Okay, that's probably the hardest thing we do today, which is not hard. The second thing is doing something, in my opinion, that you already know that AP loves to ask questions about. In fact, there's a chance that Joshua in the back is actually working on one of these problems right now. But it's so easy, I don't even care, because he knows this, right? Because he is part of the stellar senior class that is in the midst of taking a practice test. All right? So right here, this is a little bit different than what we've been doing, because what have we been doing for the past couple days? We've been taking what? Derivatives, which are slopes of the lines that are tangent to the curve. But what if I asked you to find the equation of the line that's tangent to the curve? In that case, what do you need for an equation of a line? You could use 2 points, or you could use what?
Y-intercept.
A point and a slope. Well, y-intercept's a point, right? So it didn't have to be a y-intercept, just any point, but I would need to have a slope if I only had one point, wouldn't I? What's a derivative?
Slope.
A slope. So if I give you a function, and I give you, say, this function with that x value, and you need a point, how do you get the point out of this information? Plug in the 3, and it gives you the y value, and therefore you have your point. Well, you're halfway there. Well, maybe a third of the way there. And then once I have the point, I need a slope. So how can I find a slope?
You use 3.
How do I find a slope, guys? We've been doing it for 2 days. You take the derivative. So I can do that, but the derivative, when I take it, gives me this. Am I going to use that expression for the slope? No, because that is a generic derivative. How do I find the derivative at the point that I just found? I plug in the point. Now, in this particular derivative, there's not even a y to use, right? So all I have to do is plug the 3 in. But you will eventually learn how to do implicit differentiation, and you will have x's and y's in your equation, and you would have to plug everything in. But in this case, my derivative only needs an x value. So I take that x value, and I plug it in, and I find the slope when x is 3. Well, now what do you have? You have a point from plugging the 3 in the function. You have a slope from plugging the 3 into the derivative you found. And once you have point to slope, what do? Point slope formula. And guys, don't simplify the point slope formula unless you have to. On my test yesterday, in my AP Kyle class, in both periods, I bet I had 6 or 7 people simplify after plugging the 3, -4, and the 9 in there. They simplified this into slope-intercept form. Now, amazingly, and it wasn't pretty numbers. I mean, there was like a 3.4 plugged in there and some other thing. Amazingly, nobody made a mistake. But AP, if you do make a mistake, and this is worth a point, they go 1 point for the right answer, 0 points for the wrong answer. Let's average the 2. And you lost half a point for no reason. So never change this form to that unless maybe it's a multiple choice question and you have to see which form it matches. Then maybe do the math. Are you with me on that? Just leave it as point slope form. If you do change it, I'm not going to be mad. But if you do change it and you're wrong, I've got to count off. Or you'll lose the points that you earned. Literally, that is it for the second part. So let's just run through a couple of examples. We've got a few classwork examples. So in number 1, and guys, it's really important that you label what you're doing. I'm going to show you what a lot of people do initially, and this hurts them on their AP test because they don't label stuff. I got a couple of kids, not many, but a couple of them that probably lost 5 or 6 points and dropped from a 4 to a 3, or will, I haven't finished totaling up their grade, because of form issues. Because literally, I can't give them a point because they didn't state what AP wants to see. So let me just show you examples of this. And I really think this happens because you guys have been so smart your whole life, and your teachers have let you get away with just getting an answer. So there's this scribble scrabble on your paper. It's the steady scream of like chicken scratch, just trying to get to answer. But AP gives you 1 point for the answer. They give you another point for this, and another point for this, and another point for this. So if it's not legible, or if it's not in clear, concise statements, they're like, you didn't say what that was. You didn't state this one. You didn't say what this was. Let me show you how people mess this up. So what do I need to do first? Plug in 3. How do I say that I'm doing that?
You say y
of 3, right? I know you're used to saying f of x, but you can do this with y, and you plug a 3 in. And you just state what you're doing. They don't care about the simplifying part. So 27 minus 6 plus 5 is 26. What did I just find there?
the y value.
So we now know the point, 3 comma 26. Great. You don't even have to state that. You've already said y of 3 is 26, which is another way of writing the point, right? Now what do you want to do? Find the derivative. And the derivative is 6x minus 2. What did I do wrong here?
You have to say y of 1.
I got to go y prime or dy dx. Okay? Now what do I want to do?
Plug in the point.
Plug in the point. What did I do wrong here?
It's not a derivative.
It's not a derivative. This is what? The derivative at 3. You see the difference? That's the derivative. This is the derivative at 3. 18 minus 2 is 16. So now that I have, and this is my what? Slope. That's my point. I'm ready to go. Y minus 26, 16, x minus 3. Done. But I like slope-intercept method so much better. Knock yourself out, but you're putting yourself at risk. And you might go, well, I'm good at math. I don't make errors. You're right. You probably don't. A lot of you don't make many. And that's okay. But if you do, keep in mind, there's no real reason to do it unless you have to. What about number 2? It's pretty similar, but I tell you what, in the interest of time, look at number 3. Tell you what, look at number 4 in case you're still copying number 3. Look at number 4. What do you got here? Oh, a little curveball thrown at you. I didn't give you the function. What did I give you? The derivative. How am I going to find the y value if I don't know the function? I gave you the y value. So you didn't need to find it, did I? See, I gave you the point. By the way, AP doesn't give you points like this very much. AP would say something like, they would probably just say f of 3 is -1. That's what they would say. But that is the point, right? When x is 3 on the f function, the original function, the y value would be -1. Well, maybe they say y of 3 is -1. This is actually what they probably say, y of 3. So, and you know that because this is the y function that they took the derivative of. So, now that I know the point, what do? What do I plug in here? 3. Here we go. What did I do wrong? Now, if it starts dy dx, let's stick with dy dx. So if it starts dy dx, do I write that?
No, of 3.
Now,
Clarify.
actually, you're right, but actually, I don't use parentheses when I'm using dy dx. There's a different way you write it. This is what you do with dy dx. You draw a vertical line. You with me? And if your slope has x's and y's, you can just put the point right down here at the bottom. If it only has x's in your slope equation, then you write x equal 3. So you go dy dx at 3, x equals 3, and then you show where your 3 is plugged in. Actually, they probably don't even care about this. I do it so I can see my math, but they just wanted a value for this. So you have 36 minus 12 over 4, so my derivative is 6. And then what do you do? Y
And then you plug it in the,
minus the negative 1, so plus 1 equals 6, x minus the 3. What about number 3? Any thoughts? What do I need?
You gotta plug it in first.
I need the point, so plug it in. Feel at any point in time, tell me what I'm doing wrong.
Y of 7.
Y of 7, good. Y of 7 equals 21 minus 2, 19, 28 plus 1, 29. So that's not a very pretty looking Y value, but who cares? I've seen some of the ugliest AP Y values. I've seen Y values that look like this. And you're like, really? So when I write the equation, I go y minus e to the 8 minus sine of 4 radians equals some whatever slope x minus 7. I mean, sometimes they're ugly. I would probably second guess myself and go check my math to make sure, but I don't know why they do it, but they give you some ugly slopes, ugly y values, you just roll with it. All right, I got my point therefore, right? Y of 7 is that. Now, so dy dx. What's the derivative of y with respect to x, or y prime if you want? What is that? Help me. Low. D high times 3 minus high. D low times 4 over low squared. And then what do I write the next step as? Assuming I use dy dx.
oh, you do
dy
the
dx,
line.
line,
And then you do of
x equals 7, since 7 is the only value. If there were x's and y's in there, which will not happen this year, you'll see it next year on a section called implicit differentiation. If you see that, then just put the actual point down there, 7 comma 1929. Right? So I'm plugging a 7 in. I'm going to do a lot of this math in my head because AP really only is going to give you credit for your answer, showing what you're doing, putting the value down. So I'm going to say, all right, if I plug a 7 in there, 29 times 3 minus 19 times 4 over 29 squared. And that's annoying, and I try not to do that to you on a test much. And then that gives me what, 87 minus 76 over a big number squared, I'm guessing 841.
Yep, exactly.
And that gives me 11 841s. So what is,
841s.
yeah, what is my line? Pretty ugly, right? Y minus 1929s, 11 841s, x minus 7. Okay, unless I made a careless error there, I believe that's right. Yeah, normally, like if I give you something ugly like I did on number 3, I'll do it like number 4. So even though like on number 4, you can see your derivative is going to be a little messed up, right? But what are you plugging into the derivative? X equal 1. So it's a little bit kinder on the back end. So let's take a look at number 5. I've already got the whole point. That was a nice gift, right? You don't have to find the y value. So what do I need? The derivative. So dy dx. What do you do? Talk to me. What do you do? How do you take the derivative of that?
5.
Hold up. I got something, I got a polynomial times a polynomial. If I'm multiplying something times something and each something has an x in it, it's got to be a what? A product rule. So start with your product rule. You can't take derivative of the first, derivative of the second. Remember, finding our wallet in the gym or whatever, right? You got to use the rule. Now, if this was just a constant out front, like 3 times that, you don't have to use it because there's no x with the 3. It's a constant. You could drop it down. But if there's variables with it, it becomes a product rule. So let's do the product rule. first. D second. Now, how do I do the D of that? Chain rule, right? 2 blah to the first times the derivative of the inside, which is just a 1. And no, you don't need either of those ones right there because they're not doing anything. First to second plus second times, and how do I do the D first over here? 5. Blah to the fourth times 3. So even though that's a really ugly slope, now I can say dy dx, vertical line at x equals 1. And this should be much simpler than the other one and more lines of what I'd probably do on a test. Plugging a 1 in, 3 minus 2 is 1. 1 to the 5th is 1. Plugging a 1 in there, 2 times 2 is 4 to the first, whatever. 2 to the first is 2 times 2 is 4 times 4. Still 4. Plus 1 in there, 2 squared is 4. 1 in there, 3 minus 2 is 1. 1 to the 4th is 4. 4 times 5 times 3 is 15. And I get 4 plus 60 is 64. And now that I have a point and a slope, y minus 4 equals 64, x minus 1. And I am not kidding you. You will see that question easily 3 times on your AP test next year. Which hopefully you're going, sweet, bring it. And they do it different ways. Sometimes they give you the slope, like I did in problem number 3 or 4. They give you the slope equation. Don't plug the equation in. Don't ever do that. Always plug something into that slope and find the actual slope. All right? And then finally, what is number 6? It says find the slope, the equation of the line tangent to that curve at that point. Well, at least they gave you the y value, right? So you got the point. How do you find the slope? So dy dx, the derivative of y with respect to x is, what's the rule on e to the blah? Copy it all down. Great. That takes care of the e. I don't even have to go times ln e. Like I do if it was base 4, I'd go times ln 4. Don't even have to do that because ln e is 1. What's the chain rule then tell you to do? Derivative of the top, which is just a 2. And right now I just put it there, but probably it's better to put it up front. So if you're starting to visualize these, you can put it up front. Although my keys are probably still kind of rudimentary. I just kind of write it out as it's coming just to kind of help the people that are still figuring stuff out. So there's my derivative. What do I do now? The derivative at x equals 4. So e to the what? E to the 5th times 2. So 2 e to the 5th. And now that you got your point and slope, this one actually looks pretty ugly. Y minus e to the 5th equals 2 times e to the 5th times x minus 4. Kind of an ugly looking line there, but who cares, right? E to the 5th is, I don't know, 87? What is e to the 5th? That'd be awesome. I always like to check if I get lucky. E to the 5th. Not even close. 148.
That wasn't close. But good try.
Yeah.
You were so excited too.
Yeah, sometimes you get lucky. Sometimes there's like a memory floating around in my head, and I'm like, oh, wait a minute. Maybe the memory is e to the 4th.
No, it's going to be less than 81.
That's true. Yeah. Yeah, I'm just flat out wrong on multiple levels.
Been there?
Although, if I was right, there'd probably be something wrong with me. Like, I'm memorizing e to the 5th.
You probably might. You might need to take something for yourself.
That's right up there with, no disrespect if you memorize like the first 100 digits of pi, because I realize they psych you into that stuff like in like what they bait you in and give you like a pizza party or something.
It was like we got to eat lunch outside, and I spent so much time. I don't know why.
I know.
I just wanted to like.
Didn't you
win.
get like 60?
There's always that time in your life.
Yeah, I don't know why I did that.
Yeah, there's always a time in your life, I don't know what year it is, where you go, why are we killing ourselves for a pizza party? Like, we eat pizza all the time. My kids are like, I don't even like pizza. Like when I was a kid, if you said pizza party, you're like, I'm gonna lay down in traffic for pizza party. Like, you just do anything.
That's true.
Go door to door for hours upon hours to get some, nugget of goodness from your teacher that costs nothing. At some point, the bribes don't work much. It's all about points. Points. Anyway,
Pizza party still works for me.
does it?
Well, because my mom's like a health
And like what?
nerd, and so
Oh, okay.
we like, it's an issue. Like, we get groceries from a farm in Pennsylvania that my mom has like called and like obsessed over. Like, are you guys healthy enough? Like, she's a healthy
Huh?
nut.
She may live to be
So
100.
Oh, she probably will.
Here's my theory.
We
If I
ordered
live to be
pizza
100,
from-
I have to have a much more aggressive financial plan than I do. You know what I mean? That money's got to last a lot longer.
Yeah.
So, be a little crappier, maybe go out a little earlier. Financial plan may work for you.
Exactly. It's just.
I mean, I'm actually pretty fit for a 53-year-old guy, but, you know, I don't know that I want to make it to 100. I mean, 100?
Being
Ooh.
unhealthy.
Betty White, okay, I learned today, Betty White is literally older than sliced bread.
Betty White is awesome and still has great health.
Right?
You know, like Queen Elizabeth, shockingly great health. Runs around, still keeps up stuff.
My Uncle Charles is turning 94 this week. And
That's cool.
he
Is he in great health or is he struggling?
he ran marathons into his 60s.
Wow. Yeah. Well, in that case,
My granddad.
he needs to have a good financial plan, right?
No, my.
I mean, I'm actually okay. If I go out, you know, if I retire tomorrow, I get paid more than half my salary forever. So that's actually pretty good, although that's not my financial plan. That's gravy, right? You don't want to depend on the government. What you want to do is just do wisely with your money. We'll talk about that this year. You'll think when you get that money in, I'm in better shape than I even thought I would be at this point in my life. So when I finally retire, and guys, you'll do better than that unless you decide to be a school teacher, right? So, I mean, in that case, you'll have to at least try to invest wisely, make some sacrifices. But the hope is when you finally do call it quits of whatever, and you're really just living on that money with no actual income coming in, your hope is that you can at least have what you had the day before, right? Because you don't want to go, okay, time to retire. Okay, let's tighten up the belt. Let's really be careful. Can't go out to eat anymore, honey. Let's sell one of the cars, fire the yard keeper. I mean, all these little things, you want to have a quality of life. Hopefully, it's not a whole lot different, if not better. Right? Gonna spoil your grandkids a little bit. Take them to the beach. Right? Put a pool in maybe as bait.
My
Right?
granddad
I mean, did you ever want to go to the grandparents' house that had absolutely nothing to do?
Yes.
Yes.
Well,
My
maybe I did
grandma's house
too,
is
but
awesome.
there was always there was something to do then.
No, it's just
Like
like
my
an awesome
grandmother
house
baited
to
me in with
just
like
chill at.
desserts, my Italian grandmother. We had such great stuff to eat and little things to do, but even she had a pool in the neighborhood we could go hang out at.
My grandma's house is a 500 square foot townhouse, and I still go visit her because I want to.
You're a saint. Like I did too. I went to visit them. I did, and I loved
It's
them.
also always 78 degrees in there.
Yes, I know.
It's
That's
bad.
awful. My point is though, you would have gone even more if it was like fate, heaven. Like if there was something going on there where you're like, man, I love this house because blah, 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 blah. In addition to loving grandma and grandpa,
My grandma let me cook in her kitchen,
Even better.
so that was my joy that I got to make
well, and you got to find out
really
what works.
bad jam in her kitchen.
You got to find out what that bait
You
is.
want your grandkids
One time-
to be
one
like,
time my
wow,
grandma-
grandpa's rich, let's go visit him.
Yes.
All right.
No, I want you want your grandkids to love you for who you are, but little bait, I mean, they're kids, right? Little bait never hurts. That's why they're always spoiling your kids with food and junk like that. But I'll tell you this, my wife's grandmother, when we had our third kid, we had a black 4Runner. Thanks, man. And so I went to put the third car seat. It's like, you remember Caroline, maybe if she was a senior last year?
Yeah.
And I went to put the car seat in. It was about a month before she was born. And I went and I opened the door, put the car seat in it, and went to shut the door. Would not shut. Because all three, one was in a booster seat, two were in a car seat. It would not shut. And I'm like, crap, I got a kid coming in a month, and I can't shut the door on the three. I can't go anywhere with my family. I'm like, well, we're going to need to upgrade. Well, I was looking around at Tahoes, but this is 2002. And I was looking at like 99 Tahoes, kind of used, but still new enough to be, And my wife's grandmother saw me looking. She goes, "What are you looking for?" I was like, "Yeah, I'm looking for Tahoes. You know, we need to upgrade." She goes, "I'm good. That'd be nice for your family." 2 days later, she calls me and says, "Go to the dealership, talk them down, pick a Tahoe, talk them down as low as you can get them, and then give me a call." And I was like, "What?" She goes, "Just do it." I was like, okay, went down there, found a Tahoe, talked them down as low as I could get them, still walked out the door. So they thought I was like, man, I don't know. Called her up, she walked in there and paid cash for it. That's, yeah, and handed us the keys. That's
impressive.
awesome. You know what I mean? To have the freedom to do that.
Is that your
I admire your
wife's
wife's
My wife's grandmother, and she didn't live in a fancy house. I think she lived in New Brockton, Alabama. I think they sold her house for like 50 grand. It's in the middle of nowhere. She didn't live fancy, but she squirreled some money away. Enough to buy us a brand new Tahoe. I mean, by today's, what does a new Tahoe cost now? Like 85,000?
Too much money.
It wasn't that, not 2002. It was like
The new
40,000.
Tahoe?
But still,
Like 35.
That's
in 2002, it was 39 something. But now a new Tahoe, an XL, I think it was an XLT,
Oh, okay. Never mind.
a new Tahoe loaded up with leather and all this stuff.
Dad's
Check it
getting
out.
a new Tahoe.
I
But
hope
it's
you
worth
gave
buying.
us some chocolate
I
after
refuse
that.
to believe that a new Tahoe costs like the same as a old US.
Oh.
Oh, XLT price starts at 50, but an XLT,
Why?
Evans, I'll pull one up. New LS X. Well, there's the High Country 80. So that's just a basic trim, guys. It gets worse. Here's a Premier. It says build the price. Anyway, point is, then you go in there and you start building, and pretty soon 80, whatever.
Bill,
But my point is, you financially invest, you look at it wisely, you save up, and then maybe you can be a huge gift to your grandson or granddaughter in a point where they're like, man, we got 3 kids, diapers coming out of your ears, formula bill. You know what it costs diapers a month and formula on a kid?
Diapers
Like
are really
$450, $500 a month per kid. I feel like I got a raise and my kid got potty trained. Like, please, Caroline got potty trained so early. I think she trained herself at like 2 years. She's like, I'm done. Anyway,
My
just
dad's
saying, bait is good.
car was $2,000. That's a good deal. It
You
doesn't
can
have
get a car for that.
it doesn't have a
Might not be super reliable.
It doesn't have seatbelt.
it has seatbelts in the seats that matter. And
I
then
sold a
whoever-
car mine for $300 once.
Like anyways, the people you put in the
Literally,
car,
I
don't care
paid
about the
$300.
driver.
It's my car when I first started teaching here. Such a piece of crap. So bad. $300.
My
I
lord.
put it in my wallet. You know that's a crappy car when you don't have to deposit the check. You just put it in your wallet.
What'd you say?
I said my lord to my grandma's
I just
hospital
saw,
and made me
yeah,
jam
one of the
with her.
questions on the mapping test was.
Remember
we just did
when I made 40?
tangent, it was a
Yes.
parabola to the line was tangent at a point.
Ah.
Tangent, like intercept. And I remember as I did that question, I was like, I feel like this is, like I had seen the picture on the front of that notes already. And I was like, I bet that's some like, I mean, it might be another way, but I don't know.
No, it makes some of those easier.
And you only had like 2 lines of work. And then you had to-
Right.
So,
No, that's where it's a lot easier.
Yeah.
Got knowing the calculus. Now, that being said, sometimes there's a clever way to do it too. But yeah, you'll have the advantage if you keep taking these, if you stick with this math team stuff for 2 more years and you take BC next year, you'll know all the calculus. Arguably by the time the state test happens, or almost. Because he'll probably finish up in late March, test probably late February. So you'll already know almost everything, certainly everything they would test you on. So you'll have the benefit of being good and having the calculus at your service. And
as long as I don't forget it that last year, that's the only thing that I have to be.
I doubt you would. It's so memorable. Calculus is interesting. It makes sense. It's not memorized crap. It literally, it's like, you'll really like it. It's such a great class. I wish that my students historically in AB were more interested because